part 2 then of the 2018 higher paper for triple, year 10. Satellite using communication, complete the diagram. So, recognizing we've got a station here and a station there, we're going to have to use 2 satellites and another base station there to get round all the way. So it's going to go up, it's going to come back down to a base station there, it's going to go back up and then come back down to a base station there. Explain why geostationary satellites must be used. So the thing with communication rather than geosynchronous, well, I'll answer the question. A base station can be in constant communication with geostationary satellite because it's always in the same position above the Earth's equator, whereas geosynchronous is only in contact every 24 hours. So the equator looks like we're at the top there. So the equator is around the center of the Earth. So this satellite's just going to orbit the center of the Earth, whereas a geosynchronous will take a different orbit. It'll go up and over. So it's only in communication every 24 hours. So we've got a distance. A single geostationary satellite is 3.6 times 10 to the power 4 above the Earth. They communicate with each other using microwaves, wavelength 2.8, traveling at the speed of light there, 3 times 10 to the power 8. So I've written some of these things down. Use calculation from page 2. Okay, so it's going to be time because he wants the time, and that's going to be distance over speed. So your distance is that height there, and the time is going to be that time. Your speed is going to be that speed there. Why have I times it by 2? Because it's the time it takes the signal to get to space station is going to go up and then back down. So that's why I've times it by 2 there. Let me just check. Yeah, because it wants sending from one to another. So I've times it by 2, the distance, and that's going to give you 24 seconds. It's going to take that signal. Question 6 then is kinetic theory. It's a 6-mark question, all about describing what's going on in this graph. So I've said from A to B, the temperature of the ice, so we've got ice turning into water, increases, and we can see that the temperature's on the side in Kelvin, so it's increasing as time passes. And the vibrational, or we can say kinetic energy is better, of the molecules increase. From B to C then, time is still passing, still energy being inputted, but the temperature stays the same. So energy supplies now that's being supplied breaks bonds between the molecules, which allows them to move past each other. This is going to start now turning into a liquid. Then from C to D, temperature of the water increases, and the kinetic energy of the molecules increase. So from this point, you're going to get a mixture of ice and water, but it's all the same temperature. And then once it's all turned to water, then it goes and it starts increasing in temperature. And the kinetic energy, so K stands for kinetic energy of the molecules, increase again. From D to E, the energy supply breaks a bond, so it's the same thing happening from B to C. You get that flat line where the energy is being used to change the state. It's going to allow them to escape from one another. This line is longer than B and C because more bonds are broken up here. Okay, so more bonds are broken here because it's turned into a gas, and then temperature again rises. Temperature of the steam increases, and kinetic energy molecules increase again. So 6 marker on that. Not too bad, I don't think. Just once you're familiar with it, should be okay. Specific latent heat. So that's where it changes states. Is this. That's going to be important in a future calculation. Explain what is meant by this statement. Well, it's going to take that amount of energy to melt 1 kilogram of ice into water at its melting point. So remember in the definitions for specific latent heat, and then specific heat capacity. The other one, specific heat capacity, where it takes... so if you get 1 kilogram of material, it's the energy required to raise that then by 1 degree Celsius. So a little bit different from latent heat. But now we come on to this one, and it's a 5-mark question, so quite a bit required here. So we've got a mass, which I've written there. We've got 2 different temperatures, and we've got a heat capacity. So I'm going to use this equation to calculate my energy required to raise that by 1 degree Celsius. So what I've got there now is the energy that it takes to required to rise it 1 degree Celsius. And then I need to do my latent heat one, which is up here, because in the question it says to completely melt the ice block. So we're going to take that figure from up the top. We're going to take this mass, and then that gives us this amount of energy. And then we're going to add them both together. Okay, so we're going to take, first of all, to run you through that again, we're going to find out how much energy is required to raise 1 kilogram by 1 degree Celsius. And then we're going to find out how much energy, or how much energy then it's going to require to completely melt the ice block. Question 7. You can see we've got this graph with a cut-in speed of 3.5 wind speed there. So that means nothing's happening before that speed. We've got this nice little graph. It is claimed that wind power is always useful backup, always a useful backup at times when high demand between 6 and 10. So what I've done there is 6 and 10, shaded that area and had a look. And between 1600, which is 4 o'clock, and 8 o'clock there. Okay. Is this claim correct for 4 marks? So you can see when I mentioned that cut-in speed of 3.5 there, okay, that's the wind speed it's got to be before you even start turning the turbine. You can see at 14 meters per second is this optimum, okay, that's when you're going to get the maximum output there, power output. So because this is only falling just above, it's not, I shouldn't say falling, it's just above 3.5, I've said between 6 and 10, the wind speed is just above 3.5, the cut-in speed. So the power output of the turbine will be quite low. And then after this, you can see that it's not even meeting the cut-in speed until around 7 o'clock, 1900 hours. So by that, the speed rises 4.2, which is still quite low. So I wouldn't support that claim from reading that graph. And then we've got a wind farm off the coast of Wales has an output. So I'll read the question, then I'll come back to this. So it's a rate output of 24 megawatts, connected to the national grid by transformer. The transformer now has an input coil of 400 and an output coil of 4,800. So that's your input coil, output coil. Assume the transformer is 100% efficient. Use equations to calculate the output. So we're going to use V1 over V2 equals N1 over N2. So these are the number of turns. This is your voltage. So the number of turns is okay because it tells me there that I got 400 there and I got 4,800 there for 2. But it's recognizing now that even though it says output voltage, before it goes to the national grid, that's going to be the output of wind farm will be the input to the transformer. So we're coming out of the wind farm into the transformer. So this now, 16, is going to be our input voltage, kilovolts. So I've got 16 there. Still in kilovolts there, so I'm going to leave it to 16, not convert. And then when you rearrange this equation, it comes out to 192. Calculate the output current for the transformer. So we're just going to use now power equals IV. Rearrange I equals P over V. So I've got 24 times 10 to the power 6 because I need to get it in amps. So I've got to convert now. So that megawatts has got to go to times 10 to the power 6. And then we're going to convert that now to just volts, which is 192 times 10 to the power 3. And that's going to be 125 amps. Explain the role of transformers. So even if you couldn't do all that, then we come to a nice memory question, which is explain what a step-up transformer is. It's going to increase the voltage to reduce the current, and that's 3 marks there. So by doing this, we'll decrease the energy loss to heat. Step-down transformers reduce the voltage to make it safe for consumers. Last question then, explain the purpose of an iron core. So the iron core links the transformer, and state why it's laminated. Okay, so an alternating magnet field from primary links with a secondary coil. So the iron core strengthens the magnetic field, and then the laminations, so this is worth 3 marks. So our third point there, laminations reduce the heat loss, and it's going to improve that efficiency there. So that was the last question on a higher paper. So there is a lot required for you there, but again, I think nothing that's not achievable there. So I hope you got something from this video, and thank you for watching.